where you assume something and then try to prove it, rather than doing it like a machine where, oh, it's this case, so I have to use this specific case. So yeah, ask a lot of questions. One of the students suggested creating a WhatsApp or group me type of stuff. So I'll send a link so that you can join there to talk with your classmates. And I think it's best idea that I'm not there, so I'll just post the link and then you guys can talk among each other. Any questions before we begin the next chapter? Okay. Then let's try to let me introduce you to the one of the most powerful techniques of proving something. So this is called mathematical induction. Okay. Now the goal is the following. Mm, the statements that you will often prove using induction are open sentences. So what was this? This was some statement that depended on n, and then we want to prove that this is true for all n inside the natural numbers. Okay? So our universe is the natural numbers, and then I want to prove Pn for every integer n. Okay? And for us, this is the set of positive integers. So our n will most of the time start with 1. Okay? So first, let me give you an example of a sentence, open sentence that we want to prove. So let's say that our sentence Pn is the statement. N is even or odd. Okay. So P of 1, the statement is 1 is even or odd.
So
P2, 2 is even or odd. P17, 17 is even or odd. And then we want to prove that this statement is true for any natural number n, which is super, super obvious looking. Okay. So the technique, or we call it a principle that we're going to use, is the following. Principle of mathematical induction. Okay. And we'll oftentimes simply write down PMI. It says the following. Okay. Statements above can be proved in 2 different steps. Step number 1, the basis case. Okay. And what you do is that you prove P of 1
yeah.
is true.
So I'm just gonna doesn't matter.
Now
Here.
step 2, instead of proving that P2 is true directly, you're going to make some domino effect. So this is called the induction step.
So
Okay. And what we're going
mathematical
to do
induction is strong
is that
inductions,
we're going to assume
which I
P of
obviously
n
know what this
is
is.
true for some n. Here n can be anything. And then you're saying that whenever P of n is true, then the next sentence,
With the prove
P
all
of n plus 1,
this is a starting case and a
is
general argument
automatically
showing
true.
that one case leads to the next. Electrify covers the ordinary math.
And then the idea is that if those 2 things are true, then P of n is true for all n inside the natural numbers.
Okay.
And so what does this even mean? So it's saying that by step 1, the basis step, we prove that P of 1 is true. Okay. Now, if we use step 2, because P of 1 is true,
guys.
the next step P of 2 is true.
Okay, this should be okay, right?
By step 2. And then because P of 2 is true, we can say that P of 3 is true. Okay. And then P of 3 is true, so P of 3 plus 1, P of 4 is true. And then we can basically keep going.
I should reconfigure this earlier. But hopefully,
So 1 is 2 is 2 is 3, 3
isn't
is true, 4
super
is true.
bad for
It
you
goes
guys.
indefinitely. So
Okay.
P of n will be true for all n in the integers.
Okay. This is.
Any questions so far?
All right. Just. Oops. Okay. So central idea, a chain of
All right.
implications.
So let's actually use this to prove
which
this
involves
very, very obvious statement. For all natural numbers n, n is either even or odd. Okay? And this is my fault, but I think I never actually defined what even and odd numbers are. So let me do that really quick. A natural number n is first even if n is 2 times a
Yeah, I'm
number
just reading this stuff right here. So principle of
for
mathematical
some
induction.
natural
To
number
prove
n,
that Pn is true for every natural
and
number
then
n.
it's going to be called
Step on
odd
the basis. Prove that this first
if
statement is
n
true.
is equal to 2k plus
Stop the starting
minus 1
point.
for some k inside the natural
I'm just gonna lower the volume a little bit just to
number. So first case means
can
that
prove
it's
Pn
even
plus 1.
when it's divisible by 2,
So basis, inductive step.
okay? And it's going to be called
Or
odd
this
if
inductive
it's 1 less
hypothesis, but
than an
inductive
even
step
number.
is also included as well too. So what the induction hypothesis really mean? The inductive hypothesis is most often the confusing part. When we
Okay,
say
now let's try to
assume
prove
Pn
example
is
number 1.
true, we're not assuming the entire theorem is
So I
true.
need to prove that n is even or odd
Assuming that the
for
statement
every
is
natural
true
number n.
at one arbitrary
So we're going to
location
start with the
n, so
basis
that we
step.
can prove it must be true for the next location. The structure is assume
So p of
nk
1
prove n plus 1
is
case.
true because 1, we know that it's odd, so we have to use this definition. And then what is our k? Our k is going to be 1, so 2 times 1 minus 1. So 1 is an odd number. Okay. So the basis step is super simple. 1 is 2 times 1 minus 1, so it's going to be an odd number. Now step 2, we have to use induction.
Wait, then n equals, so wait, hold on. So case 2, n's odd. So if n's odd, that means 2k plus 1 or minus 1? Why minus 1 though? That's plus 1. But, I mean, here she says she used minus 1 as your well, so it doesn't really matter. But yeah, okay, so going forward, example to some of the first n even numbers. So this equals n. Oh, I thought it's over 2, but let me see. What statement is this claiming? So let's say n, the first n even numbers. So the first 5 even numbers, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 1 second.
For the acute treatment of migraine with or without aura in adults, Nurtec ODT can provide relief in 2 hours, which can last up to 2 days. Don't take if allergic to Nurtec ODT. Allergic reactions can occur even days after use. Get help right away for trouble breathing, rash, swelling of face.
Alright, hopefully it should be okay, right? Sorry. So for some first even number. Sorry, I think my mind's kind of getting too jumbled up here. So I want to connect back to the proofs. So remember, proofs are simply a chain of sequence proving a statement, essentially. And oh wait, I mean here we're kind of introducing mathematical induction. So it's I guess in this part we're just talking about something completely different. We're still talking about proofs, so it's still under the topic of mathematical proofs, but this one is completely different, I suppose. I guess there's some elements we use like the predicate. Here, as it says, the problem we're trying to solve is we're trying. It gives us a way to prove infinitely many cases, trying to prove that yeah for all. So this is kind of a different, or sorry, a not different necessarily. in a sense that it's like a completely different category, but it's still under proof, but it's a different type of proof where it's essentially a different tool. But here it seems that like this one, we're essentially talking about it and also being practical as well. So here, it shows us how to do it. Oh, here actually gives like, okay, so suppose P has the same involving natural numbers. So we want to prove is Pn is true for every n. Okay, so here, yeah. Okay. It gives it like it's just like an example, supposedly, or central idea actually. Principle. So okay, here, okay, it gives like the algorithm essentially, and talks about induction, and then pseudocode. Okay, it's kind of what I do. It's verify P1 for an arbitrary number of n. Assume Pn is true and prove Pn. Therefore, Pn is true for. Okay, so for example one, okay, gives an example, and so basically the structure where the base case we prove a base case for the most part, then inductive hypothesis or inductive step actually. It doesn't even show the inductive hypothesis. Or here it is inductive hypothesis. Not inductive step is afterwards. Or wait. So because the inductive hypothesis contain or, okay. Oh wait, really? Okay, I never actually never knew that. So if it contains or, you gotta use. That's a good. That's a good note. Another example. I'm assuming next one is going to be strong induction. Okay, no, it's going to talk about a different case of. So yes, let's see. Overnight induction versus strong induction. Okay, this is the one I actually have struggles with. So in overnight instructions, we start from P. Sorry, we do the base case, assume Pn and prove Pn plus one. Strong induction. Uh, okay, so strong induction, we assume every single previous case are true. So from P naught to P naught plus one, all the way up to Pn. Then prove. Okay, I guess. So true strong induction when the next case naturally depends on a case earlier than n. Several previous cases. Also, I should probably mention that professor gave a our professor gave sorry said it 3 times. Professor gave us a sample, which I will do, and also do more on my. Yet sets and relations are kind of my weak point, so I gotta make sure I gotta get that down today or tomorrow. I mean, hopefully I can get since it's like 65% of our grade. I can't really I guess I'll say this until the very last, but what I will do here is I'll have AI give me like a. Oops. Plan on doing it another day. Can you please give a similar version, I guess? Funny enough, a lot of the times professors don't really give you like a exam similar to the sorry sample exam similar to the actual exam that's about to come. I really hate those, but you know. So okay, so basic set theory and set operations, which yeah, that's again my one of my weakest points. Oops, not the right exam. Let's go back here. So once you use strong induction, okay. So let's connect the dots again. Here, ordinary induction versus strong inductions. Again, we're still talking about induction, and it's still under the tools of proving. So if we're looking back, if we're trying to connect the dots, strong induction is, I suppose, related to. No, no, sorry. Sorry, I'm sorry about the jumbo. This is just how I think. I'm just trying to connect strong induction or the topics we use for this class to our main class, which is obviously my 310. Sorry, mathematical proof. So back to here. Hopefully you guys don't hear our yeah, they might, but I'm sorry. Ordinary induction. So the reason why strong induction relates to mathematical proofs. Yeah, it's I guess it's because it's another tool used to prove statements. Whereas in this case, we also use the fact the predicate for 0 to n plus 1, sorry, n, using the fact that we can also use the predicates of not just n plus 1, sorry, not just for n, but also the previous elements, or sorry, the previous values for n. And here it gives us a reason why we should use strong induction versus for instead of weak induction. I'm guessing it's gonna give an example. So writing. Let me just first read this. Use strong induction when the case naturally depends on case earlier than n. Several previous cases, breaking a number into small pieces, prime factorization, recurrence relations, coin, or postage problem. I really hate coin problem. Um, strong induction example, writing numbers as 2s plus 5t. Lecture proves that every natural number n can be written, sorry, every natural number greater than 11 can be written as such for some natural numbers s and t. This means that sufficiently large numbers can be built using groups of 2s and groups of 5s. Base case, we verified the first few values. So 11, 12, 13. And then let's also verify. Okay, so for multiple. Yeah, this is a coin problem essentially. Is I believe, was it? Sorry, I know it's the greedy problem, I suppose, that every number. I forgot the greedy problem, but essentially this is it. So yeah, let's see what they try to say. This again, we just remember this is simply just an example of strong induction. I should keep that in mind. So induction hypothesis: assume every integer m satisfying this. Why m though? Okay, so m equals. Okay, now we want to prove that n plus 1 has the same form. Because n minus 1 is an earlier number and n minus 1 is greater than equal to 11, the strong induction hypothesis tells us that n minus 1 equals 2a plus 5b for some natural numbers a and b. Add 2 to both sides. Okay. So here, so add 2 to both sides for some weird reason. Okay, that gives, wait, hold on, yeah, this is true, n plus 1. Hence, since n plus 1 and b are natural numbers, n plus 1 have a required form. Therefore, by strong induction, this is quite a, this is quite a, this is quite, uh, oh, interesting proof, honestly. I guess it works. Yeah, I gotta touch on the strong induction example. It's pretty hard to do so. So multiple base cases. Instruction induction sometimes require requires several starting cases. Suppose the induction step uses p n minus one. When proving one of the first new cases, n minus one must already lie inside the range covered by the theorem. That's why strong induction proofs are often begin by verifying p naught to p naught plus r. Okay, so the case of multiple values. All right. So inductive compare checking example. It's a lot to read.
So here, we had to assume that our P of n is true.
You might calculate P1 to P4.
In other words,
This only proves for individual statements. Does not establish P100
n
or
is even
P1000 or every possible
or
value.
odd. We don't know
So,
what it is, but we know that it's even or odd.
so common mistakes. How this connects to everything we learned earlier. Mathematical induction is not completely. Okay, this actually helps. This connects to how this connects to everything learned earlier. Mathematical induction is not completely separate from your previous proof methods. Induction proof usually contains a direct. Oh, so if Pn works, then Pn plus. Okay, so it actually does connect. Definition algebra proof of cases sometimes contradiction. For example, the lecture final contradiction argument assumes this. Then we can use that. Oh, it's factorization. So the left side is divisible by 3. This would imply that 1 is divisible by 3, which is impossible. Therefore, such intersectionality cannot exist. So the course is building a toolkit. Logic direct proofs, contrapositive, contradiction cases, and induction. Okay, so it's building a toolkit essentially. So first use logic, next use direct proof, next use contrapositive and contradiction cases, last but not least use induction.
Full coverage as low as $38 per
Um,
month with no deposit required.
Hako AI makes your daily life less lonely.
okay, so
Okay, now our goal,
let's go back to here.
n plus 1 is even or odd.
But
So here it seems that we're talking about what here?
Now I can factor it by 2.
Let's put the.
Then
Oops.
now this k plus 1 will be my new k. So n plus 1 is 2 times something minus 1. So therefore, n plus 1 is hence an odd number. So when n is even, n plus 1 is odd. And then we have to look at when n is odd. Okay, question?
Professor, so in the n is even case, can't you just conclude in the step where you write down
Okay,
which is also
let's
the
open the
definition of a
book
number,
and
then just say
see.
it's still odd? Do we have to do the like further simplifying
She
steps?
largely
Actually, no. If
she
your definition
largely
is that odd number is 2k plus 1.
uses
Oh, so
I did
examples
this.
from the
I
book,
did this because
so
my definition was 2k minus 1.
Oh, okay.
it's
Thank you.
it's a lot
And
helpful.
it was more for more
So
form of
here
practice
I believe
rather
we're
than
talking
business
about
history.
so it's 1.6 I believe. So here.
Try the n is equal to odd case. This one will be more simple, I think. Actually, this is super simple.
So 1.6 51.
So because it's odd, it has to be 2k minus 1
Wait.
for some k.
Involving quantifiers.
So n plus 1 is 2k minus 1 plus 1, which is 2k. And then this is automatically even.
I guess
So
we
this is
should
the basis step.
let's
This is
just
the
jump
induction
straight
step.
to induction, I
Therefore,
guess.
by mathematical induction, feel free to just write down by induction. P of n
Strategy for
is
constructing
true
proofs.
for all.
We still aren't talking about. What's weird?
Any questions?
I have a further question. Write down, but for n is even, we're proving that it's odd, and then when n is odd, we're proving that it's even. So by putting the opposite of it, it is true.
Because we want to prove p n plus 1, right? So let me actually fill in the details. So here, what we proved is that when n is even or odd, then n plus 1 is either even or odd.
Okay, thank you.
Okay, and Pn plus 1 is true.
She's doing this
Any
because
other questions?
remember the inductive step or inductive hypothesis, or it's actually inductive step actually, is uses a word or, which essentially you can prove it. You have to prove it using proof by cases.
What?
Mm,
Hang let's prove it.
that integer is even and so on. So because I was only talking about the natural numbers, I had to divide it as 2 key bits.
So she's another example.
This and 2. Just write down something like this. Okay, and then at the end, I have to show that this is equal to n plus 1 times n plus 2. Does this make sense? So I want to call it the induction hypothesis. And for the induction step, if you look at it, done.
Yeah, I'm just skipping through because I kind of you know, inductive hypothesis, like base case, inductive step, and so here we're proving that n squared is greater than or equal to 2n, and is greater than or equal to 2. So to prove it using this,
Any questions? So let me introduce you to the next useful tool. This is a variation of induction. Oh, sorry. So let me go back to the proof. So here, I didn't change anything here. And then I replaced n squared by 2n.
If
So start from here. This is actually side loop.
okay, so strong induction is where I'm stuck at. Unfortunately, it's like 1 a.m., so I can't really spend too much time studying.
All right, so what's different with the strong or complete induction? So it's still going to be 2 steps. So we have the basis step, and then the induction step.
I did promise myself to finish my homework
And
today,
even the
but
basis step is the same. So you're going to assume that P of 1 is
I
true.
unfortunately pushed it back
Or
today.
later we will
Terrible
see that
of
you
me.
can make this P of some number is true as your starting point. So in this example, our n sub 0 was equal to 2.
I think after the
Now,
midterm for
instead of
this
saying that P of n
class,
is true,
I
we're going to
will
say
unfortunately
P of m is true. So
I'll
assume P
start
of n is true,
doing projects
and
for
then
this
it's going
class.
to be
Or
between
sorry, like the project
1
I'm
and
currently
n.
working on. I need to
Or
kind of
some.
clarify the blueprint first.
So instead of saying P of 3 is true, we're going to say P of 1 is true, P of 2 is true, and then P of 3 is true, all at the same time. Then P of n plus 1 is true.
Okay, that's for inductive.
So what it means is that in
Or
ordinary
sorry,
induction,
for weak induction or ordinary induction, like she's called it.
we had P of n, and only then you can say the P of n plus 1. In our base case, so and it's 2s.
Here's what I'm interested in.
Find an s. Is any questions so far? Go ahead.
so
Okay. So 2s plus 5t for some s and t.
PS true for 1 equals m and then plus.
Okay,
Okay.
now I don't know where to start, so I'm going to use n for now. So for me, my n is 2a plus 5b. Okay. I don't know what my n is, but at least I know that it has to be written as 2a plus 5b. And then, if I add 1 to this, I have no idea what to do. Because like if you think about it, the previous example, what happened was that we were able to factor out something in order to get our conclusion. Or factor, so that I will get 2 times something plus 5 times something. So maybe just looking at n might have been a wrong idea. So I'm going to look at n minus.
Yeah, this is
And then if I have this, then I have 2a
she's just like
plus
trial and
5b.
error, and a lot of times this might not work.
Okay. And then we don't know this yet because the only thing that we know is that this is less than n. And then our assumption was that n is greater or equal to 11. So this will be greater or equal to 10. And then this is even smaller than our base case. Okay. So there are a bunch of different problems with this. So what I'm going to do is, instead of assuming that n is greater or equal to 11, I'm going to assume that n is greater or equal to 12. And why can we do this? Because we proved two base cases, both 11 and 12. So we can start from when n is equal to 12. Okay. Now, because n is greater or equal to 12, n minus 1 is greater or equal to 11. We can now use the induction step and then say that n minus 1 is equal to 2a plus 5b for some a and b inside the natural numbers.
I hate that I can't keep this a secret. I canceled all my food delivery subscriptions.
Now I'm going to add 2 on both sides. That exactly gives me n plus 1 plus 2. And then now I can factor out of 2. And finally, I was able to write it as 2s plus 5.
Okay, so it's again, remember, strong induction is just simply an example. So she used the fact. So again, this is p naught plus 1, and then p naught plus 2. So kind of she's using this example and inductive step. Well, so it does wait. Okay, so here she does wait, hold on. What the hell's going on here? So PM is true for 1. I don't think this is true, right? Is it? Yeah, I knew it. Okay, here, let me see what she does.
So now by strong induction, something like there does not exist. SNP set 15s plus 12p is equal to add like this.
Okay, that's kind of all we're gonna do for today. It's a short video, but